Okay, we are live. And this is the first 0 to ASIC live stream. I hope it all goes to plan. This video will be recorded, so if you miss it or you want to come back to it, you'll be able to check it later. So just before I introduce our guest, I've got a couple of things I wanted to go through. A little bit of a brief update on news to do with 0 to ASIC. So let me move over here. The main bit of news is that we submitted for MPW2, and we had 14 designs from the 0 to ASIC course make it in. That's been accepted for fabrication, so we expect the chips back in 5 or 6 months, we hope. Things went a lot easier than the first time round. I've written up this blog post and made a short video about it. And also I want to give a shout out to Maximo, who did some really cool rendering. And this is my new favorite picture that I'm now using on my website. So these are these two designs in the corner, on the bottom left-hand corner, are my designs for the course. And then the rest of the designs are from the course applicants, and the highlighted lines are the enable lines. Another bit of news is that I've got a new video that is going to be dropping soon, and that's about one of the designs that was submitted for MPW2, which was an electromagnetic fault injection detector. That video is going to drop on Wednesday, so it would be cool if you subscribed so you could see that when that drops. And what's next? Okay, yeah, so I've been wanting to do analog stuff for a while. So the 0 to ASIC course and all my experience so far has just been on the digital side of things. A lot of people have been doing analog, and I've interviewed a few people about analog stuff already. So on the website, if you go to the interview section, we had an interview with Lakshmi about her PLL design. We had an interview before that with Diego about his opamp design, and Diego submitted again for MPW2 with some updates. And Thomas Parry I interviewed about his amateur satellite radio submission, and he's also resubmitted for MPW2 with some updates. And he's got quite an interesting flow. We covered that in this interview a bit, but because there's quite a lot of interest in analog stuff, I thought it'd be cool to do this stream with Thomas. So I'm just going to invite Thomas now onto the stage. Hi, Thomas, how you doing?
Hello, I'm good. How about yourself?
Yeah, good. This is all seeming to work at the moment. I'm not actually checking YouTube, so I'm just hoping that it's going live. If people have audio and video problems, then you can drop them in the comments, and then that will let me know if something's going wrong. Maybe I should post a comment here. Comment here. So yeah, let me know if we've got audio or video problems, or if you've got any questions for Thomas along the way, then I'll make sure to get them answered. Assuming that we can get them answered, and Thomas doesn't know everything. No pressure. Great. Okay, we're getting some feedback there, so that's good.
Nice.
Okay, so I've got a little bit of some topics to go through. So I know that you've been very busy, Thomas, because you actually had 2 tape outs in 1 week, didn't you?
Yeah, I had one for the day job, and then one for the eFabless Google Shuttle. So it was a lot of work to get one submitted and then turn around and do the next one. But yeah, got them both in. So
yeah, no problems.
No, not yet. So yeah, looks good.
Great. Okay. Yeah. Who knows? There may be some problems waiting.
Yeah. Hopefully not.
Yeah. So I was wondering if you could give us a brief recap of what you did for MPW1, the satellite transceiver project, just for people who've not seen that interview. And if you haven't seen the interview, then I recommend you go and check it out another time.
Mm-hmm. Yep. So it's probably worth saying that the overall goal is to try and make a single chip solution for amateur radio satellite communication. So I don't know if people are aware, but there's many amateur radio satellites that are orbiting Earth right now, and more that are planned. And yeah, the hope is to try and make a single chip that you can basically put digital in one end, get RF out, go to the satellite, and then receive RF back and get digital at the other end. So the first shuttle was mostly checking the flow and trying to get things up and running. So on that, I had a band gap reference, which basically creates voltage and current references that are needed throughout the chip, and then also a phase lock loop. So yeah, that was on the first submission. And then
yeah, and just to interrupt you there, for people that haven't been following along, we're not expecting the results from tape out 1 until kind of August, September time. So we still don't know if things are going to work or not, but we're just going forwards with confidence.
Mm-hmm. Yep. And then this time, the main goal was to try and mature the transmit path a bit further, try and get something that resembles a realistic transmit path. So the first part of that was working on a digital analog converter. So basically supplying, I think it's 10 bits of input and then getting analog out, so differential current mode output. So yeah, design that, and then after that, an LC VCO. So basically using inductors and variactor-based VCO. So that would be used as part of a PLL. But for this submission, I don't actually have the PLL loop around it. I just have the VCO by itself, and I can basically manipulate the control voltage externally. And then an upconverter to take the DAC output, which is basically mixed with the output of the oscillator, and upconverted to about 8 gigahertz, and then hopefully driven off chip to be measured. So that's the goal for the second submission.
Awesome, super exciting.
Yeah.
So what's new in MPW2? So just before you tell us about what you've added in MPW2, there's also been changes for the analog flow in MPW2, right?
Yeah. So in reality, it's not about things that have been added, but things that have been taken away or simplified. So in the first submission, you had the Caravel chip, which was the whole chip basically with the RISC-V processor and all that, and the pad ring and everything. And you had to make your design, put it in there, and that caused a lot of trouble. And also, there was no real analog I/O pins. There was only basically a second route to the digital GPIO pins that wasn't great for high frequency or high power things. So now you can basically submit your project, just the project by itself, which is nice. It makes things a lot faster and cleaner. And there's also along the top of the chip, there's basically pure analog IOs. So you can start to get high frequency and high power in and out of the chip, which is good because I've been looking at high frequency stuff, and there's other people that have been looking at high power stuff, converters. So yeah, that's really important to be able to get that signals in and out cleanly. So yeah, it's good. And I would say generally
so we had
much cleaner.
About a 50 megahertz limit on the GPIOs in MPW1. So that's clearly a problem for RF stuff. And your particular design is meant to work at 2 gigahertz, I recall.
Yeah, the previous one's 2 gigahertz. This one goes up to 8 gigahertz. So cool. Yeah, probably 10 gigahertz is the scope of the project, but maybe try and see how much we can get out of it. But yeah.
Okay. So and that new harness is called Caravan as opposed to Caravel. Does Caravan still have the Pico RV32 RISC coprocessor, or has all of that been removed?
No, all of it's been removed. It's basically when you clone it, it's just a shell. It's just basically the completely external interface, which is good from my perspective.
Not even a pad ring?
No, it's just basically the pin connections, and then I believe eFabless combine them with the actual the actual RISC-V and everything else. But yeah, that's good. It's nice and clean.
Okay. So what was the next thing? So then we've heard a bit about what you did for MPW1 with your satellite transceiver. what are the new parts that you're testing or adding for MPW2?
Okay, yeah. So that's the DAC and the oscillator up conversion mixer. And
Okay, you just mentioned them.
Yeah. I mean, I can show some. I can share my screen and show some of the more details. The layouts are kind of nice.
Yeah, let's have a look at that. Yeah, awesome.
Yep.
Now, this is when the browsers are all going to crash.
Let's see. Okay, I assume you can see that. So, yeah, basically this is the xschem. So it's the user analog project wrapper. So this is basically the level that gets integrated into the Caravel chip. So when you get this, you open it, you basically got all the I/O already populated by, I believe, Tim. So yeah, you got all the I/O already there, and then you can start to put your pieces in and connect it up. So in here, I've got the DAC. So you can see it's basically made up of a unit cell. So this is 256 unit cells, and then basically a half unit cell and a quarter unit cell. So essentially this works with current mirrors along the top, and then digital signals basically switch this, so it's current steering. So you either have, basically you swap the direction of the current, and that's how you basically increase or decrease the current going to the output. And then you do that 256 times, plus a half, and then plus a quarter to get to your 10 bits. So yeah, that's basically the driving cells. And then in here, there's not much to look at. It's basically a synthesized, placed and routed OpenLANE design, which is a thermometer encoder, and it also has dynamic element matching. So basically, the thermometer encoder will just increment by 1 unit rather than a binary weight, and then the base dynamic element matching will scramble those. So in frequency domain, you don't get spurs that arise from offsets. So you basically mix them away, clean up the output spectrum. So that's a DAC. And then going into an RF section, I've basically got a oscillator which uses the on LVS version. Uses a differential oscillator inductor, and it's driving section to forms an LC oscillator, which can be controlled by the V control here. So that oscillator is buffered, amplifier, then goes into an upconversion stage, where basically the currents from the DAC are fed in here, and then mirrored and then commuted with the VCO LO to basically mix a signal, and then you get current outputs that are then using the loads, the inductors here, to get voltage outputs, buffered again, and then we've got a larger output drive buffer here. So yeah, it's basically taking back signals to the digital domain, mixing them with a local oscillator and driving them off chip. So that's really at schematic level. And then if we have a look at the layout, this is what we've got. So I've got 2 DACs in here, one connected to the RF chain and one connected directly out. So if we go into the DAC, you can see here the large synthesized and placed and routed section by OpenLANE. And then in here, you've basically got each of the DAC unit cells. So they consist of, it's kind of hard to see here, basically current sources at the top, and then switching devices here to switch them in and out in a differential manner, and then some control logic down here. You can see the clock routing network, which is H-tree, to basically get the same clock delay to each unit cell. So yeah, it's a DAC basically. Lots of switching currents that go combined and go into an output. And then you can see here the LC oscillator. So basically a differential inductor that was mostly modeled with ASIC from Stanford from late 90s, early 2000s. So you've got the inductor here, and then you basically got the reactor here, which is used for tuning, some capacitors here, and resistors here, current sources here. So output of the oscillator gets buffered and then gets taken to the upconversion mixer here, which then has another inductor buffered and then driven to the outside world by these drivers here. Yeah, and that's basically it. Most designs are actually replicated a couple of times, either to try and get them by themselves to be characterized, or basically this section is just the oscillator by itself, whereas this section is the combined DAC oscillator upconversion mixer. So yeah, hopefully get some good measurement results from that. Yeah, that's what I've submitted for the latest shuttle.
Well, it looks a lot more complicated than the first time round.
Yeah, slowly it's getting a bit more full. And hopefully the first time round, you will notice there's not much here, there's nothing here from the first one. But now I'm hoping to start to build upon this so that this really comes to bedrock, and then start adding more functionality to this. Hopefully we can fill up the whole area, but we'll see.
Yeah. Okay. So just to address a couple of questions that have come in, Raj is asking what tools are we using for schematic layout, simulation and verification, and I think we're going to cover all of that in a minute. So Raj, just if you have any questions after Thomas has done a bit of a run through, then feel free to ask them again. And I think Hema, if I'm pronouncing your name right, I hope, is asking about industry tools and career prospects, which I think is an interesting question. Maybe we'll get to that at the end.
Okay.
And then just related to what you've just shown us, Quan Wei is asking if the yellow and blue mesh networks are power and ground on the thing that you just showed.
Yeah, that's right. So the blue is the ground, and the yellow is the power.
You didn't have that before, did you, in the previous one? Or did I just not see it?
No, it wasn't in the previous one. Because I've got more routing, high frequency routing in this one, I wanted to put some power grids, also some ground grids, to get a nice return path for the RF. And then it looked quite nice, so I just went crazy and filled the whole chip with it, basically. Not strictly necessary. But,
did you like script that, or did you?
No, I just did it by hand, basically.
Okay.
And just I just use the array tool in Klayout just to repeat it many times. And then there's some tweaking, of course, but yeah.
Awesome. Okay. So you were going to show us like a demo of a kind of more simple analog design or flow, so that we could get a look at the tools in use and your particular flow, because you do some quite interesting things, I think, like not writing your simulation files in the SPICE language, but using PySpice, which I think is a great move as somebody who's tried to write SPICE myself.
Yeah.
So would you be able to take us through your design flow? I think that would be really valuable.
Yep, sure. So I made a project here. Let me go to. Okay, so I made this project analog design example, which is on GitHub. And then this is basically how I set up my projects. So inside of here, there's design folder, documentation folder, an environment folder, readme, source.me, and initialization file for xschem, which I use for schematic capture. Probably the first thing to mention here is in the environment folder, there is Makefile that I basically use, which has, this is a Makefile. So it basically has all the tools, xschem libraries for Sky 130, Magic, netgen, OpenPDKs, ngspice, Klayout, Python virtual environment, and xspice. So I can basically get a new environment by just running make, and then it takes a few hours, but then I've got everything I need, so it might be useful for people. Okay, so if I start xschem from here, the first thing I need to do is I need to source this file to basically set up my environment, and amongst other things, start a virtual environment. So you can see another analog design example, Python virtual environment. Okay. So yeah, you start xschem, that's basically what you get. So start off by creating a new cell. So go to design, I keep everything. So let's do opamp2. See if we've done one. So I create a new directory, opamp2. Save the schematic as opamp2. Oh, always do that. Delete that. And then, okay, right. Okay, so blank. Now you basically start to make your design. So if you do insert, you basically get the browser here. And you can see basically the xschem built-in library, the xschem Sky 130 library, and basic design, where we're doing the actual design. So let's go into here. Okay. Symbol. Okay. So let's put down some FETs. So we're going to use some low voltage 1.8 volt devices. So basically got my cursor, control F to flip it. So I've got some widths and lengths already pre-made, but we'll basically have a low GM of ID for these guys because we're going to use them as a current source, current mirror. So we're going to make basically a basic 5 transistor op amp. So here's basically going to be the, copy this, you can see, tail current source for the op amp, and then the diff pair. So here if you press Q, you can modify it, see that I've basically set the length of the transistor to 2, the width to 1, number of fingers is 1, multiply is 1, and then there's some perimeter and area things that Stefan's already pre-populated to get calculated. So for this, you want to have 2 in parallel, an M of 2. Start wiring it up like this. Then for diff pair, we want to have different mode of operation. So we're going to have a high GM of ID, make them big for offset. So basically I say small channel length, but not minimum, wide, and have a few of them. So basically make up the op amp like this. And you can basically, to create ports, press P, oh no, not P, that's cadence, press insert, home, and then xschem library, you can do IPin, and then you've basically got, and then C to copy, F to flip, Q to edit, NP. Yeah, so you can basically start to make up your circuit like this. I'm not going to do the whole thing now, but I can open another one I've made before. So opamp2 schematic. Okay, so basically the same thing. So 5 transistor op amp, diff pair, current mirror load, output device, current mirrors along the bottom. So then what you would do is one, basically go to symbol, make symbol from schematic, which will automatically make a symbol. So it'll basically find what ports are in the design. You control O, you can see there's now a symbol being created. So you open this and you can see NP and N already there because we had the ports. And then you can basically rearrange this. So I recommend that you make your symbols look representative of the function. So the one I already made looks like an op-amp. Input pins, output pin, power, ground, bias. So once you have this, you basically have your symbol, you have your schematic. You want to start testing it. So I have a test directory in my design. You can see here some I've made. So if I go to this one, Bode plot, open. You can see here the symbol. So basically now that I have a symbol, I did control insert, and then I go to the library, analog design example, design, opamp, click on the symbol, okay, I can place it. So I've placed it here. And then, yeah, basically this tests the Bode plots of load plot. So what you want to do at this level in your test bench is basically start to put the spice primitives. So you definitely need a ground somewhere so you know what the zero reference is. And you want to start putting some supplies, so 1.8 volt supply here, some bias in, bias in current. Here I'm using the AC resistors. So because I want to do a Bode plot, I want this, well, essentially like ideal capacitors and inductors. But in ngspice you have AC resistors, so you can have a different value for DC. So this DC value is 1 gigaohm, and the AC value is 1 microohm. So it's basically open circuit for DC and short circuit for AC. So that's how you can open your loop. Yeah, so then these code examples, they include basically the links to Skywater. So I think these originally come from Stefan Schipper's examples, the developer of xschem. I just copied them across between schematics, and they basically include all the models. They use basically a project variable here to say where the models are. So yeah, like I said, I just copy that across. And then another one for the simulation. So in this one, I basically set parameter temperature to 27. I've commented out operating point transient simulation. So just an AC simulation, basically from I think it's saying from 1 hertz to 10 gigahertz at 10 steps per decade, and save all. So yeah, basically we've got this now. You can start to run the simulation. So I can basically do a netlist. Having a bit of a demonstration issue here. Normally I don't get this. Right, if in doubt, close and start again. Test Bode. Okay, so netlist basically creates a netlist. So you can see here, if you go to simulation, edit netlist, then hopefully you can see the netlist that's created by xschem. So it's basically included, well, this is the actual circuit we see here. And it's included the instructions for ngspice to the simulation. It's included all the library stuff that we had from this TT models. And then it's also included all the sub-circuits from inside. So it's basically the sub-circuit netlist. So this is what gets passed to ngspice or XICE or whatever simulation tool you're going to be using. You can do simulate, and then it'll basically by default start ngspice. And hopefully it's pretty quick.
I noticed with simulation stuff that for the analog stuff, when it's loading in all the libraries it needs, that can be a big overhead of the ngspice startup. Have you experienced the same kind of thing?
Yeah, definitely. It used to be a lot worse. I think there was changes made to ngspice to improve it.
Yeah.
It's still not ideal. Yeah, so it's done there.
And the one thing that might be worth mentioning, it looks like it's starting to run now, but all that time we were waiting for then was loading library time, right?
Yeah, it wasn't the actual simulation, it was just loading the models. Yeah. I believe there's something, basically it reads in all the models and evaluates a lot more than it needs to. I don't know the exact details.
And how many corners does it load?
I think in this example, only one, because Stefan's actually only specified one.
Okay.
Because that's another thing. If you have multiple corners, if you do it the normal way of basically saying lib sky 130 TT,
it includes loads, doesn't it?
Yeah. So that's not ideal. Slice is a bit faster in that regard.
Okay.
Now that simulate is complete, you can hit waves, and then basically, it's not even how you say it. Go GAW opens, and you can see here in this browser you've got all the signals that are generated. So from this, we were interested in VAC, which is the voltage of the node AC. But you can see here it's not very good for AC simulations. Basically got your AC frequencies along the bottom, but you notice it's linear. So you can do, let's see, log Y scale, but it doesn't like it because then you've got negative values. So really you want to do basically get dB. So I don't actually use Go for AC stuff. What I use is I have different configuration. It's Python AC, Python ASCII. If I run this, so this is basically starting to go into more where things I've customized with Python. So there's basically my Python library now that I'm calling from inside xschem, and then it allows me to have control over the plotting. So I basically make a Bode plot using matplotlib in Python, and then just call that from xschem. Because as I mentioned, the AC plotting is pretty horrible. So fingers crossed this works.
That's the joy of the live demo.
Yeah, definitely. Here we go. So we've got our Bode plot there.
Nice.
So you can see just over.
Nice background as well.
Yeah,
nice,
definitely. You can actually see things. Yep. And you can see I've also got a little feature that calculates the phase margin, so that's quite nice. That's just done basically an AC simulation of the opamp that we have designed. And then similarly, you can have, so I can have one of a transient. So now they're basically a closed loop configuration with gain of 10, and then I have basically an input pulse. And here in the simulation, I've basically just got the transient. So a 1 microsecond step up to 10 milliseconds. So let me change this back to default configuration. That's actually worth mentioning in this place. This simulation configuration allows you to choose how things are running. So you can see ngspice, this is the interactive ngspice, or you can do batch with a binary output or an ASCII output, different formats for the raw file. And you can also do Zeiss, support Zeiss. I think also HSpice, but obviously you have to have the license for that. And then you can use GAW plotter or ngspice viewer or raw to VCD, so there's more for digital signals. I've never actually used it for digital stuff, but you can do Verilog and VHDL inside xschem. So yeah, go back to default, run this.
I like the way the title of that window is ngspice exited with error code.
yeah, I guess.
that definitely wouldn't put you off, would it?
No, I guess
It's probably worth saying that a lot of these tools are fairly rough-edged.
Yeah, they are. I mean, I think ngspice is rough-edged, but it's also really nice once you get used to it. It's smooth to operate, and Stefan has done a lot of design himself before, so he knows what matters. So yeah, this is a better example on Geo because it will be time domain where I think it really excels. So I can select some signals. So we can put V in. So basically a square wave centered around 1 volts with 50 millivolts up and down. And then I can plot the output. And yeah, we can see it's not quite 10 times gain, but yeah, there is some gain there. And then you can zoom in and out. Not much to see in this signal, but in other simulations there might be. And you can add other signals. May not be anything interesting happening in these. So yeah, that's basically xschem simulations and how I make my designs, the schematics for my designs, all inside xschem. But one of the problems is it's quite difficult to get more complicated simulations because there's not a way of organizing different conditions, like different corners and things like this. And there are things that are built into ngspice, but I don't think they're very nice to deal with, and also tie you into the ngspice way of doing things. So the other thing I do is I basically have some Python libraries. So it's basically a library that is called, if I go to this project here, you can see it's an environment. This is a submodule to the library. So it's YAADE, which was supposed to mean yet another analog, automated analog design environment, just to come up with a name. So in here, there's different tools. Probably the most important ones, spice tools, where basically there's a whole load of functions that you can see there's quite a few functions. And the idea here really is to create simple interfaces to the simulator, but try and keep the oddities of the simulator out of it. So this is kind of like my generic object or class. And then basically for ngspice, which is the most developed at this point, this is meant to basically inherit that class and add the ngspice specific elements. So the idea is that you can basically choose ngspice or Zeiss or Spectra, which is the cadence simulator, and basically do things like set parameters. You can make it more descriptive rather than horrible spice-like instructions. So as an example, basically, yeah, so I've got these, started using PyTest, basically to make some continuous integration testing. So in this PyTest test, basically specify the netlist, so the schematic that I want, and then I say that I want to generate the netlist, and then I pass that netlist to my ngspice interface. And then here, say I want to do basically a temperature sweep from -40 to 125 in steps of 55, so only three steps. And then basically what I do is I find all the MOSFETs in the design, and set the operating point conditions, basically to save the operating point. Run the simulation over a whole lot of different conditions, and I have this tool to check the operating region. So basically what this does is it make sure that all my MOSFETs are basically all the MOSFETs I want to be in saturation region, maintain in saturation region over basically temperature and any conditions I want really, but commonly temperature, voltage, and corners. Another example here is basically we do the same test we just did, the AC simulation, but do it over temperatures or corners, temperatures, and currents. So probably not much point in running these now, which will take a while. But that's basically how once I've got the basic simulation up and running, and start to cover more conditions. And the intention is to have some self-checking so that you can basically do pi tests at the top of the project and check that everything still looks good. I'm not quite there in regard to making 100% self-checking, but this intention. And then, of course, you can basically start doing automated documentation at that point as well, which is another thing I want to look at, but don't have currently. Yeah, so that's kind of an overview, very high overview to the Python interfaces that I use.
And is this in your example repository that you put together?
Yeah. So it's a separate repository I have in GitHub, but it's instantiated as a submodule.
Okay.
In the example, yeah.
Excellent. Okay, so we've seen schematic capture and some simulation. And then what is the next step for you?
So once you're pretty sure you've got a good schematic and you're happy that it simulates well, performance is there, then you start doing layout. So my main tool for that is Klayout, as you've already seen. So basically my approach would be normally I have everything in a single design, but for this we'll just create a new layout. Yeah, it's fine. Okay, so yeah, basically an empty layout here. I've got the Sky 130K layout technology installed. So at this point, basically I need to go back to my schematic. We're saying that basically E descends into this subcircuit and control E descends or comes out of it. Yep. So now basically I've got the circuit here, so I need to make the layout for it. Kind of split my screen a bit here. Okay, so what I'd basically do, and this is a bit that also needs some improvement, but I generate the devices in Magic and import them into Klayout. So basically what I do is I go up here.
So Magic has these series of macros where you can say I want a MOSFET of this size or this type, and then it will do the generation of that for you, right?
Yeah, exactly. So if I do over Magic here, okay, so devices, and I want to make one of my low voltage NMOSs for my diff pair. So NMOS device type, low voltage type, and then my width was 10, my length 5, and I don't want a guard ring. I want to make it without a guard ring, so I just deselect this box, and I create and close, and then basically got my device here. So now what I want to do is basically write that out to GDS. So I have a folder here, Magic Devices, so there's something special about that. You can see I've already made it here, but I would basically make the name of the device with the dimensions included, so it's obvious what it is.
Are those the most important ones? Speaking as an analog newbie, are those the most important ones, the length, the width, and the number of fingers?
Yeah, definitely. I mean, I'm not sure that you have much control beyond that. But yeah, definitely the width and the length, and then how many you have, whether that's as a multiplicity factor, i.e. m, or as number of fingers. It's basically the most important things. So I mean, there are other things here that are really around the edges of ratios of like diffusion and things like this, but they're really second order effects, or maybe even third. So yeah, basically now I've created this, I'd basically go into import and other files into current. So you can see I've already done this. This is basically those devices I generated. I can just instantiate them here. So just import. And basically at the moment, by default Klayout is just abstracting everything. So I can hit the asterisk key. It shows everything. And then for some reason, these layers aren't being mapped correctly. So I can hit the sky 130 again to reload that. Okay. So now I've basically got my devices here. And then basically, yeah, the fun can begin. So let's say that I was going to lay out these this diff pair as a cross quad. So basically splitting them with half the devices of one, half the, let's say, yeah, devices of one transistor here, another half up here, and then vice versa, basically to improve offset and mismatch across the die. So I select it.
And this knowledge that you have about the best way to lay out the physical devices, that comes from your years of analog experience?
A bit, but also it's relatively straightforward to learn if you're inclined. So I mean, probably the best, most practical book is the CMOS Design by Jacob Baker, I think. I think that's probably the best one to just cover everything. So that will cover things like matching, as well as some circuit things. And it's like, yeah, you can basically, there's also a fair number of famous ones, the art of analog layout, but that's much more deeper in scope. But yeah, you can most of these things you can find out in textbooks if you just read them. But being exposed to other people also helps.
Yeah, absolutely.
So here I basically want to have, I'm going to make 2 rows and 10 columns so that I get my 20 devices in total. So my row vector is going to be 0x offset, and then let's make it 12 in y direction, and let's make it 2, 0. And basically I've got all my devices. Yeah, so then now basically it's a matter of settling in for long haul and starting connecting these things up.
So is that, have you done much PCB design?
Yeah, I've done quite a bit of
So
PCB
is this kind
design.
of now similar to just filling in the blanks on a PCB? You've put your components where you want them in a way that makes the routing make sense. And now you're going to draw lines to connect them all.
Yeah, essentially it's quite similar in that way. The only thing that's noticeably different is that there's not as many nice aspects to the tools. So they're very expensive.
Auto-route.
Yeah, there's no auto route, but there's no what do you call them, fly wires either.
Ratsnest.
Ratsnest, yeah. So you kind of have to keep the connectivity in your head. Also, the design.
And then if you get it wrong, then you would get an LVS fail at the end. But otherwise, you'd never know.
Yeah, exactly.
Okay.
And the trouble there is at the end, so it's gonna be quite painful.
You've already done all the routing.
Yeah. So there are tools, professional tools that can help with that, but even then they're the more expensive of the professional tools. So even when I'm doing this at work, I wouldn't have those features. Just have to kind of do it in your head.
Interesting. It's interesting that it's so kind of far behind PCB layout.
Yeah. I don't fully understand why, to be honest, but I mean, it's a bit more complicated, but not so more complicated that it's not further ahead than it is. I think it's probably just the small number of, or small market, but maybe that'll change. So
Maybe you can show us just drawing one of these lines.
Yep. So let's say I want to connect the rest of the sources of these guys. So I create my path, select my layer, and then basically choose I want to start, and then you see it's snapping to 45 degrees or 90 degrees. So it sticks 90 degrees. Just go up and draw it up. I usually change the color in this, and then get rid of some of these. Yeah, and then basically you can just align it as you want, and then you really want to try and make as much use of the tools as you can. So I know, for example, that my spacing was, I think it was 1.8. So I know there's 10 columns and spacing is 1.8, and then bam, all of them. So yeah, basically that's the best way to do layout. My impression is.
And I guess you have to draw all the vias by hand as well. You don't get like on a PCB where you can just change layer and it will automatically drop a via for you.
Yeah. So well, I've made what we call a pcell generator to make vias. So I can basically insert and I can choose what layer I want to start on. So in this case, let's say I want to start on metal 1, and then it'll basically put the vias and then the top and bottom metal. So that's a bit nicer than having to do each via by hand, especially since they have to be an exact size.
Cool. Okay.
And then yeah, then it's basically many hours connecting everything up and getting to your final layout.
And then, okay, so then that's kind of the final part then, really, isn't it? Let's just say that you've finished this now, and now you want to verify it against your design.
Yep. Well, probably the first thing you want to do is DRC is we probably want to do DRC as you go along, but I'll show this first. So there's two DRC methods. One is inside Klayout. So basically I can run this, and this comes from basically the open PDK's repository. And this will run a DRC in the Klayout environment, which there's some important reasons to that, because the way that Magic reinterprets a layout, when it reads it in, it can sometimes hide mistakes. Well, not hide mistakes, but it reinterprets it, and inside Magic there's no problem, but in the original GDS there is a problem. So that was one of the issues I had with the first submission. But now I use Klayout DRC, which helps a lot. It is a bit slower though, as you can see. There's not that many things in the design, but it's still working away.
How long does it take on your full design for your transceiver?
Maybe about 45 minutes. A long time, basically. Yeah. It also depends how you handle cells and hierarchy, and influences it quite a lot as well. But you can see here that, well, looks like we have some errors. So I go to by category. These are basically all the design rules, and the green ones are okay, but those ones here are saying it's a problem. So what's it saying? We're clicking it, saying the minimum area on metal is this value. So yeah, fair enough. Normally you would have a connection there, which would make that minimum area larger. So yeah, basically you can go through and find your errors and fix them. You can see there's quite a few different rules that need to be checked. So that's basically my first DRC step, where I do it as I go along. And then the second one is, if I go to, let me go to my submission. Okay, so I have these basically bash scripts. And they allow me to basically easily run DRC or LVS in Magic. So see here, I basically just supply a cell name as an argument, and then it basically goes into opens Magic, reads the GDS, loads the cell, flattens the cell, and then I can start looking at DRC. So if I run this, run DRC, let's do DAC unit cell. Should be relatively quick. Okay, so it's opened up Magic. Has it worked? No. Oh, nowhere. Sorry, 2 seconds. So one. So this is my main repository. So if I do the same thing again, quite slow for some reason.
Yeah, actually, we'll take the opportunity to answer a question from Tom McKay, who's asked what class of PC is being used.
Class of PC. Oh,
as in, like how powerful, I think.
Terrible is the short answer. I think it's about 8 years old and not very powerful when I bought it. So yeah, it's not indicative of the program. It's more the fact that I haven't bought a new PC. Yeah, basically it's loaded the DAC cell. But anyway, what I normally do is go to DRC and basically run the DRC for Magic, and then typically I would get a couple of different DRC errors, then I would get in Klayout. And the approach I take is if I can get both of them DRC clean, it's probably likely to be pretty close. And anything else that eFabless find with a proper caliber license, I can fix as needed. So yeah, was meant to be DRC. LVS is done quite a similar way. There's no currently that I know of anything inside Klayout for LVS, although the engine doesn't look good, but I don't think anyone set it up. So for run LVS, basically, maybe I should. Some idea, but basically it goes and gets the cell, loads it in Magic, extracts it for an LVS, and then basically runs xschem, exports netlist.
So it creates a tickle script that Magic will read, that loads the design and then does a circuit extraction, writes that to a spice file.
Yep.
Okay.
And then tells xschem to generate a spice file as well, and then uses netgen, which is another Tim Edwards program, to compare them.
And that's the netgen is also the same program used in the OpenLANE flow for the LVS at the end of that.
Yep.
Okay.
So if I do run LVS DAC unit cell, we'll basically go extract it from Magic. And I also have another script, which is the parasitic extraction, which is a very similar thing. It's just a tickle script that provides the inputs to Magic to create a netlist, but with the extracted elements.
And I guess you're going to explain that in a minute, aren't you? Because at the moment you're doing validation, but on kind of connectivity, and then afterwards you're going to run a simulation with ngspice of that extracted netlist, including parasitics, and check that that's still within your design parameters. Is that correct?
Yep, exactly. So, well, in this case, you can see that LVS has failed, which is a bit suspect. I need to look into that. But anyway, tell me that circuit 1 has 17 devices, whereas circuit 2, so I think circuit 1 is the layout, circuit 2 is the schematic. So there's a mismatch there. You can see the number of devices. You can maybe see what it is. Yeah, so it's an NFET a number of nets don't match either, so you can basically then start to try and debug what goes wrong, has went wrong, and this typically can be a very painful process, but it's life. So yeah, I'd basically do the same thing to do a PEX, so parasitic extraction. Basically do the same thing, and then I'd get a net list. So what I can do is, let's do this. Show you an example. Cell test. So here you can see basically that dark unit cell. Let's see if I've changed the symbol, but anyway. So what I've got is I kind of have two different cells. One's a normal one, and one is the PEX. So the normal one, if you descend, should be the circuit. Yep. And then the PEX one, if you descend, I've basically just created the code block and just copy and pasted the extracted netlist into it. But by putting it in ngspice, I can basically just, it looks the same from a higher level. I can change between them. I'd like to make it more automated so that the PEX script automatically creates the PEX symbol, but currently it's just by hand. So yeah, once you've got that, you can basically run the same simulation, which will undoubtedly be slower, but will provide more information.
And then you would get these plots out at the end, like the Bode plots that you mentioned earlier. And then do you just compare them by eye, or do you have some kind of automated system to check that things are in bounds?
No, at the moment it would probably just be more of a check by eye type thing. It really depends a lot on what the circuit is and what the simulation is. Yeah, maybe with something like a Bode plot with the phase margin, you can automate that quite easily. But the other things, it might be harder. But yeah, you can decide what's important to you.
Cool. Okay, awesome. So I think that's about the whole flow, isn't it?
Yeah, I think that's basically it. At the end of it, you've basically got your GDS that you upload to GitHub and then tell eFabless about, and then that's it, you're done.
And if there's questions about submitting to eFabless, then check the video by Jeff from eFabless, who showed how to do the application. So we've got a couple of questions as we went through that I have been saving, and some questions that I got from LinkedIn as well. So I think from Ali Reza, we've seen the design process, what tools are used, and how DRC and LVS is done. But he's got one more question at the end, which I don't think we've covered, which is an electromagnetic simulation done for the passive components, such as inductors, capacitors, and transmission lines? If yes, how, and based on what software?
So no, short answer. There's currently, as far as I'm aware, that information isn't, well, there's two aspects. One, I don't know of an open source simulator that does it. But even more fundamentally, I don't think that information is available for the PDK. I haven't seen it. I haven't seen really any current limits on any metals. So there's kind of rules of thumb that people use, but I haven't seen anything actually documented. So yeah, can't be done really, unfortunately, at this stage. I think you just have to use a bit of engineering guesstimation, really. Okay.
Probably not the answer he's hoping for, but
yeah.
That's what we've got. Okay, and some questions that we didn't get to during your demonstration. Somebody asked how many bits wide is your DAC?
10 bits, yep.
That's an easy one. Did you have, so you work as a career doing this kind of stuff. Mm-hmm. So what's your perspective on like knowledge of the open source tools and how that could relate to job prospects and career opportunities?
Well, I'd say that it's important not to get caught up in tools. Keep mindful of what you're actually trying to achieve, and the fundamentals of design are the same whether you're using open source tools or commercial tools. So I think really if you focus on the real design principles, it doesn't matter too much about the tools. I mean, tools generally are easy to learn, especially if you're in an environment where you've got a colleague that knows what he's doing. You can just reach over and ask them. I think if you're trying to start working, if you can talk really knowledgeably and intelligently about the design process and choices made, that's much more important than saying I've used X or Y tool. So yeah, I think
because it's usually fairly easy to transition to different tools, like a PCB program. I've used lots of different ones, and you get over the differences and you get back to productivity quickly. But it's So would you recommend more like people get hold of that book that you recommended and practice laying out some circuits and do some simulations, and that will give you the knowledge?
Yeah, definitely. I think the best way is to find some project which is hard but achievable, and then just work on trying to achieve that, to fulfill that project, and you'll be surprised how much you learn along the way.
That's basically what I did with the digital side of things. So I want to do some analog next time for MPW3. So Gabrielle is saying, can you quickly recap the overall workflow? So I'll let you do that.
So I guess there's a step that I haven't even shown here, which is the first step, step 0, which is decide what you want to design. If you've been really good, you can maybe write some documentation about it to begin with. And then probably step 0.5 is you want to look at your basically your models. So you want to look at the devices available. So you want to do some simulations and characterize your transistors or passives if they're important to design, and get an idea of where you want to bias things. And then doing the design proper, basically I use xschem to do schematic capture, and then simulation, and then basically some iteration around that. And then towards the end of that, it'll move more from a design informing simulation to verification, to making sure that the performance is covered over everything I need. And then once you're happy with the schematic, then start layout, and basically lay out your cell. Run DRCs as much as you can, so that you don't end up with a big mess at the end. Then run LVS, another DRC, and then parasitic extraction. Some circuits it doesn't matter so much, but some it does. And then maybe some more verification, and then you're essentially done for that cell.
And then is that the end?
Yeah, I think so. Well, I mean, you tape it out, and then you measure it, find all the mistakes you made, all the false assumptions. But
Okay, so we've got a question from Manikanden. How to implement the current sources in the circuitry of an op-amp and how to check them practically. I think you kind of covered that with your current mirror and the layout that you did for the op-amp demo, but maybe not the how to check them practically. Maybe that's an interesting topic you could get into a little bit. You've got your chip back, now how do you check them?
Well, I think there's also another step before that, which is how you check it in simulation. And there you really want to have a look at the operating point of the devices. So basically in the BSIM models, there's lots of parameters. So an important one is the VDS sat, so saturation voltage, so how much voltage you have to have between the drain and source to basically keep the device in saturation. And you want to check that you're meeting that. So you want it to be, for current source, you want that to be quite high. So you want to have a low GM over ID. And then you usually want to check that the VDS sat is high, the GM over ID is where you want it to be, and that you have enough margin. So really that involves putting in the operating point, saving commands into ngspice and evaluating them. And currently that's a real pain. Hopefully we get a better solution in the future, but you basically just have to, in your spice command, write out a big string of the device name that you want and the parameter you want, and then it'll pop up in your spice results. You have inspect it. Yeah, and then basically there's quite a lot of literature on how to bias transistors for current mirror or differential pair or something. So you may want to check some of that out. But yeah, basically, yeah, ngspice and operating point evaluation. And then depending on how you design your device, it's probably unlikely that you're able to measure a specific current mirror in a chip that's returned. Usually it'll be hidden away somewhere. But you can also do test structures, so you can basically place a current mirror just by itself and measure that if you thought that was valuable. But, yeah.
Okay. And let's finish off with a final question that we got from Tom. He was saying, how do you verify the VCO that you did in your transceiver? Can you simulate phase noise? It's a bit over my head, that one.
Yeah, so there's no, as far as I know, there's no open source way to do phase noise at the moment. So ngspice has an experimental
Maybe you can
periodic
just
steady
explain
state.
what phase noise is for those of us
Yeah.
who don't know.
So phase noise is basically, maybe it's more familiar to people, is jitter. So if you imagine a digital clock, you basically have your clock, and the edges won't be perfectly aligned, and there'll be some jitter. They'll move back and forth. So phase noise is basically the frequency domain.
The digital world isn't perfect. Thomas.
Yeah, no, shocking. So phase noise is basically the frequency domain equivalent of jitter. They are really the same thing, but in time and frequency domain. So when you have a VCO or an oscillator, there will be some, rather than being a perfect, basically just a single frequency, there'll be some skirt around the frequency, but basically the frequency of oscillation is varying over time.
So if you put, say, like a perfect sine wave in, and through your opamp or whatever, or your VCO in this case, and then you look at the output on a Fourier transform, on a frequency plot, instead of being a single line output, you've got a little envelope around it.
Yeah, exactly.
The width of that would be phase noise.
Yeah, so there's a few different measures of it. Typically, it's basically how much power it's down from the carrier per some offset frequency. So it's a thing that's very heavily researched in academia for good reason. But it's difficult to simulate because it's like a cyclostationary noise. Because normally when you do a noise simulation, it's an AC simulation, so it comes back to those operating points of the devices. So in BSIM, they'll basically say for this bias with this current, for this voltage, all the parameters on the device, you'll get X amount of noise. The trouble with an oscillator is that it's basically changing through lots of different states at the same time. So you have to use a tool like a periodic steady state simulator that finds the steady state, and then, I don't know the exact details, does some magic to get the total noise over that period of oscillation. And I guess there's some involving in frequency. I don't know the exact details, but it's not a simple simulation to do. So I don't know of a way to do it open source. There is a free tool by a researcher in Italy that can do it. I've not got it up and running yet, but I need to have a look at that. But yeah, short answer is not easily at the moment.
Not yet. Watch this space. Maybe by the time we get to MPW6, we'll have it.
Yeah, hopefully. I would like that.
Cool. Okay, Thomas, thanks so much for your time. I really appreciate you coming on and sharing your very valuable knowledge. And
yeah, no problem.
For people that want to find out more, then you can check out the design example that Thomas has put together. And I think you'll be adding a few more bits and pieces to that in the coming weeks. So yeah, that's it from us. hope you all enjoyed it and you learned something, and see you on the next video.
Cheers. Bye.
Bye-bye.